well, the third comment is important because it's going to set the stage for what's coming later, is that there exist, physical quantities or a physical quantity that is represented by finite dimensional representations of the angular momentum algebra. That is, L's are not suitable for them, are not suitable to describe them. However, these observables satisfy the same abstract algebra, although their structure is not the same as L. So we write them as, say, JI, I1, 2, 3 in general, and they satisfied the algebra that the commutator of Ji and Jj is I h bar epsilon I jk jk. Okay, and these observables have no classical analog. They're kind of angular momentum, but they don't have classical analog, and they're called intrinsic spin or just spin. Historically they were called intrinsic spin, but now they're just called spin. Okay. You guys have heard of spin, right?
Yes, sir.
Yes,
okay,
sir.
good. So the thing is that spin does not arise from the motion of the particle. And therefore, it's not angular momentum in the usual way. Classically, and also quantum mechanically, angular momentum comes up because of rotation, right? Spin does not come from rotation. It does not. It is something intrinsic, okay? And therefore, it cannot be represented by L. So what we're going to do is we're going to find, so our project for today is that find the finite dimensional representation of the angular momentum algebra, which is given by, let me write it again, Ji Jj is equal to I epsilon I jk jk. Here what we're doing is that we are setting h bar to be 1. So we're choosing units in which we measure all our angular momentum in terms of the fundamental Planck's constant. We can always do that. Okay, so let's do this. So, these are three equations, three non-trivial equations. There are a few trivial equations here. So J1, the commutator of J1 and J2 is I times J3. Commutator of J2 and J3 is I of J1. And the commutator of J3 and J1 is I J2. Okay, these are the three equations. Now, we can construct another operator, not an axial vector operator, but a scalar operator out of these three guys. And this is called the J squared operator. And it's taken by taking J, the vector operator, and taking its dot product with itself. And of course, this is by definition, say, J1 squared plus J2 squared plus J3 squared. And it's a simple exercise to show, and this is something you have to show by yourself, is J squared commutes with all the J's. So J squared commutes with J1, J2, J3, okay? So we have a set of 4 operators. We have a set of 4 operators. And these operators are J squared, J1, J2, J3. Sometimes I might write Jx, Jy, and Jz, okay? So of these 4 operators, how many operators can I choose that are mutually commuting?
You mean how many pairs?
No, just how many operators at once.
Oh, okay.
You gave me the answer, though. It's a pair, right? I can only choose 2 who are going to commute with each other. I cannot choose more than 2. Okay, so let's choose. It's conventional to choose J squared, of course, you have to choose it. And you can choose Jx, Jy, or Jz, J1, J2, J3. Let's choose J3, okay? So they're going to commute, right? Is that clear?
Wouldn't there be a third bracket? I mean, like commutators.
Oh, yeah, this is a set.
Oh, okay.
Yes. So, yeah, of course, this is also true. Okay, I'm not using anti-commutator here. Yeah, I know, it's confusing. Brackets are like, have you guys read Through the Looking Glass, Alice Through the Looking Glass, and what she found there?
No, sir.
Okay. Well, there's a joke there about words, working overtime to mean many different things, because Humpty Dumpty wants them to mean many, many different things. So words have to work overtime. So on Sunday, they have to come around for their payment. And so brackets are like the words, but in mathematics, they have to mean a lot of different things. So it's a very nerdy joke. So what this means is that you can find eigenfunctions which are simultaneous eigenfunctions or eigenstates of these 2 operators, right? So
Yes,
simultaneous eigenstates or kets or functions. Now, they're going to have the same J squared eigenvalue, though, all of them, because everything commutes with J squared. So sometimes we'll forget to point out the J squared eigenvalue, but let's not forget that right now. So J squared acting, say, on a state alpha m gives me the eigenvalue alpha. So alpha is the eigenvalue of J squared. So we want to find out what alpha is. And we want to find out the Jz eigenvalue, which is m. Okay, so we want to find out alpha and m. This is our problem. And in the yeah, so this is basically all we have to find. So, because these are all physical observables, we assume that these are all Hermitian, right? If all the components of J are Hermitian, that means that J squared is also Hermitian. So, but for the sake of analysis, it's very, very useful to introduce some non-Hermitian operators. Let us define them. Let's call them J plus and J minus. And they're the complex linear combination of J1 and J2. And from the definition, you can see that if I take J plus and take its Hermitian conjugate or adjoint, I get J minus, and vice versa, okay? Because J1 and J2 are Hermitian, but I, under Hermitian conjugation, becomes minus I. So these two guys switch. So now we can recast the angular momentum algebra that we wrote here, over here, in terms of J plus, J minus, and J3, okay? So in terms of, it becomes J3, the commutator of J3 with J plus just gives me J plus. And the commutator of J3 with J minus gives me minus of J minus. And the commutator of J plus and J minus gives me twice J3. Okay, so this is very easy to show, but you should show it nonetheless.